Okay. So in a study for the all seismic, earthquake, and all the related informations, you understand that our main source of information is the recorded data, right? So that means seismogram is our only information that we have. We have nothing. We cannot see the earth inside. We cannot do anything uh, with the earth interior. But what we can gather is the seismogram, and from that seismogram, we had found out all, right? So basically, whatever is our nature of understanding about the earth interior is all from the study of the seismogram, because that's the only physical basis. And so that is why when we put the seismogram all over the earth, or might be at the accelerometer all over the earth, this becomes our laboratory, and that is where we collect the data. And from that data, we try to understand what is going on underneath the earth, right? So that's our information. So everything we can do, either the location of the earthquake or nature of the faulting or whatever you do, is we have to start from the seismogram. So the seismogram, if it is the source, then it propagates through the medium, right? And then it is being recorded on a seismogram, right? So that's the part. It's very simple to understand. But the problem is this, that whenever it's recorded on the seismogram, it also records the noise of the place, right? And that noises are basically anthropogenic noise, cultural noise, all the things are there. So our seismogram is a complex in nature. And so we have to go for some sort of a data processing of the data, a data processing of the seismogram, before we try to address the problems, right? So then we address the problem and try to understand from the seismogram. We try to data process and then try to find the seismogram. Then we use the data processing things, understanding the propagation path things, and we do the inverse analysis to go from to calculate what are the sources, right? So all the things. So if you can call it as a direct problem, so that means from the source to the medium and the seismogram to the data processing, if it is a direct problem, from the process data, we can come to these are the informations we will be try to derive, and that is our inverse problem of the natures, right? So so our work is basically, so this is our total information system, right? And from there, we can do the monitoring for the local level, for the regional level, for the global level. The local levels are basically for addressing some of the local issues. Say suppose if it is a site response, or how the site behaves during the one part of the town from the other part of the town, or one part of the city to the other part of the city. These are the local problems, right? So that we need to know, because as I told you, from our engineering seismology point of view, if we need to build a very big buildings, or a very multi-millionaire dollar or multi-millionaire rupees type of construction, then we need to know very accurately how this building will behave in case there is a big earthquake in that local regions, right? So we need to understand that. So that is where we need to give the input parameters to the engineers help them to design, because we are the geophysicist or seismologist. We can give the engineers the parameters. And on the other hand, the engineers also needs to know how to utilize these parameters to betterly design the structure or the bridges or the buildings in order to have a earthquake resistant structures, right? Or this one. So these are the local level things. And then there is a regional level. We need to understand how much is the what are the actual which fault is more active, how many earthquakes are coming per year from that fault, what is the range of the magnitude of these things. And so these are the regional level type of problem. And then there is a global issues. If there is a big uh, nuclear detectors or the nuclear explosions, we also need to know. And also, if there is a big earthquake that can be magnitude like 9.0, 9.1 type of magnitude earthquake, which you have seen it few years back in the Japan, or few days back in Kamchatka area. So these are the global earthquake which can capable to make some of the, say suppose the 2004 Indonesian earthquake has changes the earth rotation speed. So that is also a big regional thing. So that is what we also monitor the things for the changes of the global scale. So these are the seismic monitoring. Therefore, all the aspects are necessary. And of course, a person cannot do all the things. So a person gets specialized in some of the other areas. Say some do the regional thing, some do the research on the local level, some might be the global type of things. So so then we can calculate the seismic hazard of the area, seismic hazard of the place, and then we try to understand the seismic source mechanism. One area it is a normal faulting, how the source signal behaves. One area is a transform faulting, much more predominant, than how that area behaves. So these are the seismic source mechanism. Then we also need to understand how from the earthquake record, how the crustal structure behaves. So what are the earthquake velocity, density all over the say along the crust, earth crust, and where is there is any discontinuity or not. So these are the crustal and deep earthquake. And then we have the another branch, which is the data processing branch, which basically try to understand how the process data can be improved, or how to get your much more better result from this inversion analysis with a much better process data. So this is also a data processing things. So these are all of the different part of the engineering seismology. Everybody is not used to do all the things, but some part will be done by somebody, and they might be of interest in that. Now, interdisciplinary subject, we also try to do this earthquake hazard. The insurance company also take the data from the earthquake hazard, try to calculate the risk, and then insure your buildings or the structure based on that risk of that area. They demand more money if your building or the structure is located in a very earthquake-prone area. So they also do a lot of research on that. The nuclear hazard, say suppose in 2011, the Japan earthquake created a very big implication on the Japan nuclear reactor waste material storage area, and that has been mixing up with the water of the ocean. So that was also a very big concern. So the nuclear studies, so the seismic studies also help in the nuclear reactor monitoring, and it's basically the day-to-day functioning, right? So So these are the different disciplines which we can get. Now, first of all, we need to understand that during the time of an earthquake happen, there is always a seismic wave generated, right? So these waves are coming from the seismic source or the earthquake source, and then it passes through the material of the earth and recorded at the surface, and that's our model, and that is where we have to analyze, right? Now, so let's see, this is your focus. This is your seismogram recorded, and the waves passes through that. This is your P wave and S wave. I'm coming to that point. P and S wave, so they are, so this is your time mark. And so from the earthquake source, we can only measure at the seismogram when the P wave will arrive and when the S wave will arrive, when the surface wave will arrive. So P and S wave passes through the body. P and S wave passes through the body. So that is why we call these waves as a body waves. And the surface waves passes all over the surface of the earth or very near to the surface of the earth. And these are the surface waves. So you can see from the pictures of this seismogram that there is a lot of information. The lot of information in the sense why these things are like this, why these things are like this, why the surface waves looks like this, but why the P waves and S waves looks only this much, why the surface waves looks like this way. So these are the information. This is not a just like a that okay, it looks like this for this particular earthquake, but it may not looks like for a different earthquake. No, it will have a consistent pattern, and that we need to explore, right? So, so this is our record. So waves is just like your if you throw a stone in the pond, it will create a wave, right? We call it as a wave. Now, what is a wave? Anybody? Disturbance in the medium. That's good, but in a physical sense, what is the wave? If from your physics knowledge, what is the wave? In a physical sense, what is the wave? In front of your physics knowledge, what is the wave? Find a wave. But what is the difference between waves and the vibration? What is the wave and what is the vibration? Nobody. You know, big physics, right? So physics, it's a physics. So if vibration is only a time-dependent phenomenon, right? So it is a sine over the t, right? So it's only a time. But so it is a sine over the t, right? So it's only a time. But a wave, it has a both time-dependent as well as a space-dependent phenomenon, right? So a sine 2 pi by lambda into x minus v into t, right? So there is a x part, which is the distance part, as well as there is a time part, which is which is how that behaves with time. So that means if you fix the things at this point, then you will be seeing at a particular time, then you will be seeing that different places, the waves or the things are vibrating like this way, right? So they are different displacement, right? But if you see a particular space, then at a different time, it will be looks to be different. So a wave is a space-dependent and time-dependent phenomena, right? So now, so the sound wave and speech. The sound wave is a speech. The way I am talking is also a wave, but it's a sound wave, right? So earthquake is also a wave. An earthquake is also generating a wave. Now, when here my vocal cord creates the vibration, here the locked fault creates the vibration or the ruptures. We call it as the ruptures. Now, sound wave propagates through the atmosphere. So between you and me, the sound wave is propagating, and here the sound wave is propagate, or the earthquake waves is propagate through the earth, right? So the ears are recording the vibration, and in the seismometers records the vibrations, right? And the brain process the recording, and when here a seismologist process the recording, which you call it as a seismogram. So there is a similarity between the sound and the earthquake waves, right? So wave is a disturbance that transfer the energy from one point to the other point. So where you hit, where the stone hits the water, that point it has been transferred the energy, but then as the times progress, it transferred that energy to the next particle, and next particle, and as a result, the wave propagates, right? So, so light is also a wave, sound is also an wave. So what is the difference between they are periodic in both space and the time, right? So space means they have a wavelength, and the time means they have a period. So we have a both wavelength as well as the period. That is important for us, right? So wavelength is a measure of the spatial width of a wave. So that means it has a unit of length. So a wave has a wavelength, and the period has a unit of time. So that is what you call it as a second, right? So the inverse to the period, we call it as a frequency. So this is 1 by second is equals to hertz, or cycles per second, and amplitude is a measure of the height of the wave, and it has a unit of centimeter of meter, right? So wavelength, period, frequency, and amplitude, that is the 4 factor we will be deriving, right? So from your physics, this is the wavelength. If this distance, this is the distance. If it is the time, then this is the period, right? So then that is your wavelength, and this is your per second, or the second will be the time period part, right? So this wave will travel with a speed, and that is what we call it as the wave speed, and that is what we also try to do in an earthquake. This rupture will propagate with a velocity, and that is what we call it as a rupture velocity, right? So just like your sound velocity, we also have a rupture velocity, and that it's always takes some finite amount of time for the rupture to arrive from the source to the stations, right? So that time is very important, and that we need to calculate, right? At closer distance, the nonlinear wave propagate can result the amplitude dependent propagation velocity. Now, this is a very, very interesting subject, what we like to do, because sometimes the earthquake are a huge earthquake, and the recording station is very near. So when I'm talking about very near, it means we are talking about around 50-kilometer distance from the epicenter, right? So less than 50-kilometer distances. So then we have seen that the amplitude of the wave is basically depends on the velocity of the wave, because as the velocity changes, the amplitude is also changes, right? Now, we will come to that point about how the nonlinearity affects the propagation, but there is a nonlinear behavior is noticed if it is a very short distance of the recording. But if it is a long distance, then it becomes all linear dependency, right? Now let us see that. So when the seismic wave propagates, we call it as an elastic wave. Now, why it is an elastic wave? Because our rock is an elastic material, right? So because the rock is the elastic material. Why we call the rock as elastic material? Because if you give the force to the rock and then you take out the force from this, the rock, just like your any elastic material, it come back to its original positions, right? So the rock behaves elastically if it is under pressure, right? And when it gives the pressure, it deforms, and we get or if it ruptures, then it provides the wave, which we call it also an elastic wave, because due to the elastic properties of the material, these waves are being generated. So this is called elastic wave. And then if there is a non-elastic type of wave, we call it as a shock wave, right? So the shock wave and the elastic wave, these are the two parts which we need to analyze, and the non-linearity of the material is due to the shock wave. The elastic wave behaves linearly elastic in manner, right? So now the earthquake generate the seismic waves or the elastic waves, but in addition to the earthquake, these seismic waves can also be generated due to the volcanic eruption, due to the nuclear explosion, due to the wind, due to the traffic noise, due to the sonic booms, due to the human movement, can also produce the seismic waves or the elastic waves. The human movement or the noises has also produced the seismic wave, and that seismic wave and that properties can also be explored in order to calculate the earth structure, right? So that is your noise or the microthermal recording of or might be the noise recording with the help of a seismometer, and that will be also analyzed to calculate the earth structure, particularly very near surface we can understand. Now, as an engineering seismologist, our main emphasis is to understand the very near surface of the earth, because that structure is more important, particularly the uppermost 30-meter soil or 30-meter of the earth crust is very important for the engineering analysis. And that is why we are more interested as an engineering seismologist, the upper few meters of the site. The deeper part is okay. That might be the seismologist jurisdictions to do, but for the engineering seismologist, upper few meters is very important for the structures, right? Because all our engineering codes and everything are more or less based on the upper few meters, say suppose 30 to 100 meters type of depth is very important for us. Right. So now, as I told you in the very beginning, that when I show the seismometer or the seismic record, you have seen that the P wave and S wave looks different, but the surface waves looks a completely different pictures, right? So that different pictures means basically the frequency content of that wave. So the frequency content of the body wave, frequency content on the surface waves, they are different, right? And we need to understand what is the frequency level of this recording during the time of an earthquake. So a frequency understanding in addition to time of recording is very important, right? So we are interested first to record the seismometer, record the seismogram and see with time all the variations of the P wave, S wave, and the surface wave arrival time. That part is fine. But then also we need to find out the waveform of the P wave and S wave as well as the surface waves in order to understand what is the frequency content of the material or the recording or what frequency get energized when we have recorded some particular earthquake, right? So it is just like if you put a prism in front of a white light, you will see the different lights, right? So basically all the VIBGYOR, so that means violet, indigo, blue, yellow, green, and this one. So this type of color you can see. So similarly, if the seismic wave comes and recorded on a seismometer, we can see the different frequency of the waves, right? So that is what we also need to do to analyze this part, right? So as I said, that the part of the wave which passes through the body, we call them as a body wave, and we call them as a P wave and S wave. And part of the wave, when there is this disturbance reach to the surface part get also energized, and it is called surface waves. And the surface waves are the lab waves and the Rayleigh waves. So these are the four pictures, or the four type of seismic phases are very important for us to understand. So one is the P wave, one is the S wave, and the other is the lab wave and the Rayleigh waves, right? So if you see any earthquake record, then you can see that all our earthquake records, as you will be touch upon this point again in the future, that we have a seismic recording. The seismic recordings are always three-component recording, right? So we always record the north-south motion, the east-to-west motion, as well as the vertical motions, right? So this three-component recording of the ground motion at any point, we always make. Now, earlier days, when we are in the 1930s to 50s or 60s, in that time we have only one component recording. So basically, we are at the time interested on the earthquake location. So earthquake location, if it is your issue, then only one component is fine, because that will be giving you the P arrival or the early arrival of the waves, and we can calculate all the things. But we are also interested about the S wave arrival, try to understand heterogeneity of the material and all these things. So gradually now, all the three component recording are basically used. Now, three component recording, we have as I said, that typically whenever we set the station, we always orient one sensor either in north direction or in a south direction, depending upon how you orient it. Usually we try to rotate it towards the north direction. So if one is the north, the instrument design is such a manner, then the other will be in the east direction, right? So basically north, if you put one sensor in north direction, other sensors will be in east direction, and another is in the vertical directions, right? So north, we call it as a north-south motion, east-west motion, and the vertical motion. Now, north-south motion and east-west motion, these are the two horizontal motion, and the V is the vertical motions, right? So this is usually we put it like this way, because we do not know from which direction earthquake will come. But whenever the earthquake has been registered into a seismometer, we first calculate where the location is, and from where the location is, if I know, then I can calculate from that location that location to the center, that is your radial direction, and that location perpendicular to the radial is a transverse direction, and the vertical direction. So radial, transverse, and vertical. So the advantage, there is some advantages. The advantage is this, that we can we can calculate the P wave very nicely if we have a radial part, and the SH wave is very nicely if we have a transverse part. So that's the different issue, but we can do that. Okay. So here we have a three part. One is a radial, one is transverse, one is vertical, because they have rotated it. So north, south, east, west, and the vertical, now they have been rotated to calculate the radial, transverse, and the vertical, right? So that is being rotated part. So this is vertical, radial, and transverse. Now, if you see it here in this, just a glimpse, you can see the vertical part recorded the P wave arrival very, very distinctly compared to the transverse part, right? So the transverse part, you cannot see any P wave arrival, but the vertical arrival is a very. So whenever you try to locate the P wave arrival, we should always see the vertical component, right? The vertical component will give you the P wave arrival very distinctly compared to the either the radial or the transverse. Now there are some part of the radial is also there. You can see the some part of the radial still has a P wave, which is important to know, because this wave is basically a P wave, S wave converted P wave. So basically that is your SB part. So that we can use that. But let us see. Don't go to the much more complicated level at this stage. But let us see the S wave. If you see on the other end, the S wave is very energetic into the radial part compared to the vertical part, and compared to the transverse part is also there, but the radial part is more energetic. So we will be seeing the S wave arrival either from the radial or from the transverse. We will not take the actual reading for the S wave arrival at the station from the vertical component, because that may be a little bit delayed, right? But either the radial or the transverse will give you the better results. So this is your SV wave and this is your SH wave. We come to this point afterwards. So yes, remember this one. Now, if you can say that the lab wave and the Rayleigh waves, lab wave is distinctly appear in the transverse wave, right? You can see the lab wave appear, but the same thing you cannot see it here, right? But you can see here there is another surface wave. It is called Rayleigh waves. So Rayleigh waves is very distinct in the radial component as well as the vertical component. So if you need to identify your Rayleigh waves, you always see the either the radial or the vertical, right? Don't try to find out the Rayleigh wave in the transverse part, because that you cannot see it, right? So the transverse part, there is not at all the Rayleigh wave, but the transverse part has a lab wave, right? So you need to understand which component or which type of seismic phase you can see in the seismometer or in the seismogram, right? So a surface wave and body waves, if you analyze it, then the surface waves is a large amplitude waves. You can see it here. This is a very large amplitude compared to the P wave, S wave. So surface wave is a very large amplitude. So whether it is a lab or Rayleigh, it doesn't matter. They are very large in amplitude, right? And the frequency. So what do you think the frequency? Is it a very high frequency or it's a very low frequency? The surface waves? Right. So high frequency means what?
and it's and we don't it's just go to press. And less than 15 hours. The vibration constant
in vibration per second. So basically what? So
conditions per second that it's higher.
so that means these waves are high frequency wave or this is a low frequency wave?
Free. So you can go to the morning streak side. It looks like that whole vibrations happening on.
So this is a
Speak cluster. There's a speak factor things in most so it confident is for highly frequency.
high in frequency, right? So these surfaces are very high frequency parts compared to these waves. So these waves are much more low in frequency, right? So you can see here. So high frequency means it's a basically the wavelength is long and this is a very short. It's a basically the wavelength is long and this is a very short wavelength, right? So this is okay. So if you can see it here, which has a highest wave speed, P wave or the Rayleigh waves?
But
seeing the record, what do you say? The P wave has the highest velocity or when the Rayleigh wave has the highest velocity? Huh? Why?
No, see, about the
it reaches fast, right? So that means it reaches fast. So therefore, since it reaches fast, then this one, so that means the P wave has the highest velocity that S waves, right? But the Rayleigh wave has also a less velocity than that of the but the Rayleigh wave has also a less velocity than that of the S waves, right? So the lab wave and between the lab wave and the Rayleigh wave, which one is the highest velocity? More velocity than the Rayleigh waves, right? So therefore, all the waves are coming with a different types of the waves are coming with a different types of velocity. So that we need to understand, right? So therefore, the surface wave in general travel slowly, but the body waves travel much more quicker manner, right? And so the surface waves are not produced by the deep earthquake, right? Because if it is a very deep earthquake, as you can see it from here, if it is a very deep earthquake, then the surface wave generation is very feeble. So that means the wave which reached to the surface is already died down. So therefore, that surface wave is not a very important or is not a very energized in the recording stations, right? But if it is a very near surface earthquake, then the surface wave will be predominantly high, right? So that you can always see in the record. So this is what I was trying to emphasize on you, that for us seismologists or engineering seismologists, we have only thing is the record. So from the record, we can understand all the evidences, what is going on in that, right?
So that was the base. Shift was up the space, okay, which is by where we can say we put it.
Right, of course, right?
That's probably talking.
Oh, I see. Yeah. Let me see. It has to be the short wavelength. Yes, this has been opposite. Okay, yeah. Thank you for pointing it out. Yeah, right.
Thank you.
So seismic wave type. So first of all, let us do the body wave. So in general, there are two types of waves. One part is the compressional part, and other part is the shear part. Because whenever the rock ruptures, rock has ruptured as the compression, and then there is a shear. So there are two domains. One is the compressional domain, and other is the shear domain. Now, the compressional domain produces the P waves. and also produce the Rayleigh waves. In the surface side, the compressional part is produce the compressional surface wave, which is the Rayleigh waves, and the shear waves is due to the shape changes, and that will be producing the love wave as well as the S wave in the body. So the shear surface wave is the love wave, and the body surface, body shear wave is the S wave, right? So now, compressional body waves. So we are talking about now the body waves, not the shear wave. Compressional body wave, we call it as a P waves, right? So P stands for primary. We call it P as a primary. P is a body wave because they travel fastest and are the first to arrive at the recording site. Although, please remember, P and S both generate at the same time at the source. So at the source, the P wave and the S wave generated same time, same spot, right? But since the P wave travels faster, it supersedes the S wave and reaches to the surface, reaches to the recording much earlier, right? So the P waves travel to the solid, liquid, and gases. All the things, the P wave is a compression, so it can passes through the gas, through the liquid, through the solid. P wave can pass through, and within Earth, P wave can travel up to 14 kilometers per second in a very in the deep interior. But on the surface, P wave has a velocity 5.6 to 5.8 kilometers per second, right? So that's your P wave travel speed. Now, so it goes. So if you see that the medium is just like all the particles are like this, and if you hit by a P wave, so some part get compressed, some part of the media get basically relaxed, then some part is again get compressed, some part is again get relaxed. So there is a movement like a worm. See, that means there is a compression, then there is a rarefaction, compression and rarefaction. So the P wave propagates like this, and this is the direction of propagation, and the particle is also vibrating in the direction of propagation. So the P waves, all the particles are vibrating in the direction of propagation, and the waves are moving like this way. So P waves are therefore a very high speed wave. So if you can see here, there is some of the places when it's a compression, then the next material get much more relaxed, then it is again compressed, then it's again complex, and then this is all your undisturbed medium. So this is your relaxed mode, and this is your compressed mode, right? So particles are moving in the direction of the propagations. Good. So these things you can see it here in the radial and the vertical component. The P wave arrival is very well marked, but the P wave is not in here. Okay, the shear wave or the shear body wave, we call it as a S wave. So S wave means S wave is not surface waves. Please do not make these things that S wave is a surface wave. S wave is a body wave shear part, right? So S stands for the secondary, or it is called the second fastest wave then after the P wave, and it is always comes after the P wave, and within the Earth, the shear wave speed is 8 kilometers per second in a deep interior, but on the surface, it is 3.4 in that kilometers per second, right? So whatever the velocity, that depends upon the rock type. Different rock the S wave velocities are different, right? So if you see the shear wave, so if this is your undisturbed medium, right? And if a shear waves come, then the shear waves will produce the vibration in the direction perpendicular to the direction of propagation. So if it is the direction of propagation, then the particles are vibrating perpendicular to this one, right? So therefore, if you see a wave is propagating like this is your wave propagation, then the particle can vibrate like this way because this is 90 degree, and the particle can vibrate like this way. This is also 90 degree from here. So this is one of the, say suppose this is a horizon. So if the particle is, if the wave is moving like this way, particle can vibrate in this manner. So therefore the particle have in this horizontal plane, and the particle can also vibrate in a plane perpendicular to the direction. So this is also a perpendicular direction. So this wave, we call it is a horizontally polarized wave because this is in a horizon, right? So this is called horizontal polarized wave, or we call it as the SH wave. And this wave, which is perpendicular to the propagation, so that is why we call it as a vertically polarized wave, right? So SH and SV wave. So S wave can divided into the two parts. One is a SH and other is a SV type. So this is the horizontally polarized and the vertically polarized because both are perpendicular directions, right? So this is your if you see that wave, then this is your the way it is being moving, the secondary waves. So this is your amplitude of the waves, and this is the wavelength of the shear waves, right? So particles will undergo non-coaxial. So because these things are moving in this direction, particle vibration is not along that axis but perpendicular to the axis. So it is a non-coaxial, and there is nothing volume change, right? So this is your P and this is your S. I told you this is the compression and the dilation, and this is the two part. Okay. So if you can see here, after P waves, all the things before rally wave, whatever is this thing, these are all different S components, right? I will explain you this is phases, different phase of the S wave. So this is called S wave, HCS, SS. We'll see it. What are the things? And then there is a Rayleigh wave and there is a lab wave, right? So before that, all the S waves will arrive before the surface waves. So this is what I called it as a SH wave and the SV wave. So this is your vertical plane. So this vertical plane, whatever the phase content in the vertical plane, so that means this vertical line, this is called SV. This is the horizontal line. This is your S wave, and this is your ray, right? Okay. Okay. So lab wave, so shear surface waves is called the lab waves, right? So shear surface wave is called the lab wave. So the lab wave is generated due to the shear motion. Okay. So these lab waves are faster than the true surface wave, as I shown you earlier, that the lab waves appear earlier than the Rayleigh wave, right? So that is what you have seen it here. Lab wave appears earlier than this one. So basically, therefore, the lab wave is a shear surface waves, right? So and then you can see that you can see this property This is called dispersion. Let's get the engineer code. Okay. We can then do it afterwards after the things. Okay. Thank you. So just a minute, 1 minute. So this will be the physics. This is what is called as a dispersion. So you know from your physics what is called by dispersion wavelength, right? So basically these are the different wavelengths, and that different wavelength propagate with a different velocity. So that different wavelength propagate with a different velocity. So that is a dispersion characteristics is present in the surface wave, both as a Rayleigh as well as in a love wave. So that we will be also looking into it. Okay. So that's another thing which we will utilize to calculate the velocity under the deeper structure, because high frequency get attenuated very near surface, but the low frequency surface waves can go much deeper. So that means the dispersion property of the Rayleigh wave will provide you the structure of the Earth, and that will be also encountered in our next study, and that is our next class jobs. Okay, so thank you. There will be a lunch now.